In this video, we will learn how to use volatilization gravimetry to calculate the quantity of analyte in a sample, or to determine the formula of a hydrated compound. What is volatilization gravimetry? Volatilization, which comes from the word volatile, means the conversion of a substance or substances to the gas phase. Typically, a sample, whether it be a compound or a mixture, is either heated or allowed to undergo a chemical reaction, and the volatile components are liberated and are thus separated from the remaining components of the sample. Gravimetry or gravimetric analysis is an analytical method used to measure mass or change in mass to quantify an analyte. Putting these two definitions together, we get a new definition. Volatilization gravimetry is a mass analysis method that uses thermal or chemical energy to separate substances in order to measure their masses. If the mass of the original starting sample before separation is known, and the volatile components are driven off through heat energy or a chemical reaction, then the mass of the substances remaining after separation can be determined by weighing the vessel. If we then find the difference between these two masses, we get the mass of volatile substances liberated. This simple calculation is the main principle of volatilization gravimetry. Examples of volatile compounds which may be released during chemical or thermal decomposition of a sample include nitrogen gas, chlorine gas, carbon dioxide gas, and water vapor. Now let's have a look at the loss of water vapor from a hydrated salt as a specific example of volatilization gravimetry. When a salt contains water molecules within its structure, we say the salt is a hydrated salt. Water molecules that form part of a salt crystal lattice structure are specifically referred to as water of crystallization, or sometimes water of hydration. For example, the hydrated salt copper-2 sulfate contains water molecules within its structure, giving the crystals a blue appearance. The formula for this compound is CuSO4.5H2O. Commonly, hydrated copper sulfate has 5 water molecules within its crystal lattice per 1 formula unit of copper sulfate. The correct name of this compound is therefore copper-2 sulfate pentahydrate, although we often just refer to this compound as hydrated copper-2 sulfate. We can determine the mass of water of crystallization in a salt such as this using volatilization gravimetry. If we know the mass of the hydrated salt and we remove the water of crystallization using thermal energy by heating, the water will escape as a vapor, leaving behind a white powder. This is dehydrated copper-2 sulfate, or anhydrous copper-2 sulfate, where anhydrous refers to a salt that does not contain water of crystallization. So anhydrous copper-2 sulfate has the formula CuSO4. The mass of this dehydrated salt can be determined by weighing. The mass of the anhydrous salt is smaller than the hydrated salt because of the loss of water. The mass of this water lost can be determined by the difference in the masses between the hydrated and dehydrated salts. The balanced chemical equation for this reaction is CuSO4.5H2O solid being heated to give CuSO4 solid plus 5H2O gas. Incidentally, this is a reversible reaction in reality. The reverse reaction is promoted by the addition of water and cooling. The setup of this volatilization process is as follows. An iron ring is clamped to a retort stand. A clay triangle is placed on the iron ring, and a crucible containing the hydrated salt is placed onto the clay triangle. The contents are strongly heated. The crucible lid is left slightly open to allow water vapor to escape. Periodically, the lid is put back in place, and the heat is removed, and the crucible is allowed to cool. The crucible and its contents are weighed and the mass recorded. Successive heatings and coolings are repeated over and over until the mass of the crucible and its contents is constant. At this point, we know that all the water has been removed, and the contents of the crucible appear white instead of blue. This unchanging constant mass of dehydrated copper sulfate is what we will use in calculations. Volatilization gravimetry is also useful to determine the coefficient for the water of crystallization if it is unknown. Since we know the mass of the starting hydrated substance, and because we can determine the mass of the dehydrated salts after heating to constant mass, we know that we can determine the mass of water vapor which was liberated during heating, and that this is the same mass value as the mass of water of crystallization in the original hydrated salt. We can then determine the molar mass of water, and using the mass and molar mass together, we can determine the number of moles of water. We can use the key equation number of moles is equal to mass divided by molar mass. Then we can use the number of moles of water to determine the number of moles of the hydrated salt. We can do that using the molar ratio, 1:n. We are going to practice this type of calculation in a moment. But before we do that, let's look at one more useful piece of information we can get using volatilization gravimetry. We can also use the various masses determined from a volatilization experiment to calculate the percentage of water of crystallization in a hydrated salt. The percentage water of crystallization in a hydrated salt is equal to the mass of water of crystallization divided by the mass of the hydrated compound times 100%. And we've already seen that these masses can be easily determined using volatilization gravimetry. Now it's time to practice. A sample of cobalt-2 chloride hydrate COCl2.XH2O is heated until its mass remains constant. For every 1.00 grams of cobalt-2 chloride produced, 0.831 grams of water is liberated. What is the value of X, where X is an integer? And we are given the molar mass of cobalt, 59 grams per mole, for chlorine, 35.5 grams per mole, for hydrogen, 1 gram per mole, and oxygen, 16 grams per mole. We are told that a hydrated salt, cobalt-2 chloride, is heated until constant mass. The name cobalt-2 chloride hydrate and the formula do not tell us how many molecules of water there are per unit of cobalt chloride. We are only told the number of moles of water of crystallization in terms of X. Heating a hydrated salt to constant mass typically involves heating a salt strongly in a crucible with the lid off to allow the water of crystallization to escape. The reaction equation for this process is COCl2.XH2O solid being heated to give COCl2 solid plus XH2O gas. Over time, all the water of crystallization is removed. The hydrated salt is converted to an anhydrous salt. An anhydrous salt contains no water of crystallization. During cooling and weighing, the lid of the crucible must be in place, and this is to prevent water vapor from the air re-entering the crucible. This is important because this reaction is reversible and we want to prevent the reverse reaction from occurring, otherwise the masses of each substance are unknown. We need to ensure that cobalt 2 chloride is indeed fully anhydrous. To solve this problem, we can put the data that we are given and that which we need to find into a table. This table is not absolutely necessary, but sometimes it helps when we are dealing with a lot of information. We are told that for every 1.00 grams of cobalt 2 chloride produced, so let's put this mass into the table under COCl2, 0.831 grams of water is liberated. And so this is the mass of water. The words "for every" tell us that 1.00 grams of cobalt 2 chloride and 0.831 grams of water are not necessarily the actual masses of these substances produced, but rather the ratio in which they are produced. We know that the stoichiometric coefficients 1 as to x is the mole ratio of these substances. So first we need to convert the masses of these products to moles. We start by calculating the molar mass of cobalt 2 chloride, which is equal to the molar mass of cobalt plus 2 times the molar mass of chlorine, since there are 2 chlorines. Substituting in the molar mass of cobalt, which was given to us 59 grams per mole, and that of chlorine 35.5 grams per mole, we get a molar mass of cobalt 2 chloride of 130 grams per mole. We can put this value into the table. The molar mass of water is equal to 2 times the molar mass of hydrogen, because there are 2 hydrogens, plus the molar mass of oxygen. And these values are given to us. So substituting 1 gram per mole for hydrogen and 16 grams per mole for oxygen, we get 18 grams per mole, the molar mass of water, which we can put into the table. The next step is to calculate the number of moles of cobalt 2 chloride and water. We can use the key equation number of moles is mass divided by molar mass. So for cobalt 2 chloride, taking its mass and molar mass from the table, we get 1.00 grams divided by 130 grams per mole, which is equal to 0.00769 moles. For water, the number of moles is equal to its mass, 0.831 grams, divided by its molar mass, 18 grams per mole, which gives 0.04616 moles. Since the ratio of the moles of cobalt 2 chloride as to water are the same as the stoichiometric ratio 1 as to x, we can now solve for x. How we do this is we take the moles of cobalt 2 chloride as to the moles of water and divide each value by the moles of cobalt 2 chloride. These two values cancel, giving us 1. The moles units cancel on both sides, and solving this division here we get 6.00166. So far in this calculation we have not rounded off, but now it is time to do so. We need to round off to a value with no decimal places. Since x cannot be a fraction, we cannot have a fraction of a water molecule, and we are specifically told that x is an integer. Finally, we get an answer of 1 as to 6, and this is the mole ratio of cobalt chloride as to water. These values are also the coefficients in the hydrated compound formula. Therefore, the value of x is 6. And the formula of the hydrated compound is COCl2.6H2O, which is cobalt 2 chloride hexahydrate. Let's summarize what we've learnt about volatilization gravimetry. We learnt that volatilization gravimetry involves separating volatile compounds from a sample and measuring the change in mass. This quantitative analytical method can be used to determine the mass of the remaining non-volatile substances, and from this, the mass of the liberated volatile substances. We looked at specific examples of hydrated salts, where the remaining non-volatile substance is an anhydrous salt, and the liberated volatile substance is water vapor, which comes from the water of crystallization in the hydrated salt. And these mass values can be used to determine the number of molecules of water of crystallization in the hydrated salt formula. We also briefly learnt that volatilization gravimetry can be used to determine the percentage of water of crystallization in a hydrated salt.